So I'm going to be talking about amorphous polymers or conjugated polymers and the role of defects for trapping charges. So amorphous polymers are defined as polymers that have no crystal lattice structure under X-ray or electron scattering. But in my research, more specifically, we'll be looking at conjugated polymers, which are polymers that have alternating single and double bonds that allow for electron transport through them. So they act as semiconductors or like metals that allow for electron flow. And defects in these polymers are caused by a few different reasons, but a lot of the time they're caused by strain or intrinsic defects or deviation from optimal bonding configuration. And research in thermal energy transport has been studied on these defects, and it's been found that these kinks in these polymers or defects limits the efficiency of thermal energy transport through the polymer. And so I'll kind of look at that kind of same thinking, except with conjugated polymers and electron flow. So my first thing I'll look at is the rate of reaction. And so we'll take the initial momentum and then convert it to kinetic energy, and then from kinetic energy to temperature. And then once we have the temperature, we'll take the rate at each temperature along the span of the graph. And so this rate is the first order kinetics, and the PR in the equation is the probability of transmission to the right-hand side of the model. And that corresponds to the probability of the product side of the reaction. So just take a normal chemical equation, and you have the reactant side and the product side. And so this is the percentage that it will end up on that product side. And that's calculated by taking the probability at each point on that right-hand side and summing them all together to get this probability graph. And the purple line is the probability of the PR on the right-hand side at each time. And the second thing we'll look at is eigenstates and energies using the Hamiltonian, where Vx is the potential on the system. And in the kink polymer model, Vx will change based on how wide or how deep that kink is modeled as. And then this figure is just an example of a test run with eigenstates and their energies. And so here we have some movies. And if you watch, the kinked polymer will have a larger buildup right before that kink, compared to the non-kinked will have an even more even distribution. As you can see like right now. And the second thing we'll look at is energy states. So here are graphs of the energy values at different excited states. So here we have the ground level energy, and then we have numbers on the side that correspond to the level of excitation. So for the non-kinked polymer, we have a standardized, if you look at a particle in the box standardized model, it will follow it exactly. So we have at excited state 3, n equals 4, you'll have n minus 1, which is 3 nodes, and it just follows a perfect pattern all the way through. However, in the kinked polymer, you see we have an overlap in 2 and 3, and this is caused by degeneracy, which is when you have more than one eigenstate at the same energy level. And this is caused more often than not by symmetry of, usually in the Hamiltonian, you have a symmetry of the values you put in, so you get the same energy level for different eigenstates. And this is more easily seen if you plot the energies of each eigenstate. And if you look at the kinked, it moves up in like a stair-step pattern. And this is another way of visualizing that this is a degenerate. And so further, oh, I missed the slide, didn't I? Okay, rate of reaction. So analysis at realistic temperatures was very important because at a higher momentum, we have temperatures that are just completely unrealistic. And so taking a group of 6 points that have a realistic temperature between negative 50 degrees Celsius and 100 degrees Celsius, we see and plot them on this graph with the rate of reaction and then the inverse temperature. And so you see that the kinked polymer at each individual temperature has a smaller rate of reaction individually. But if you look at the slope of the lines, it also has a smaller slope, which means that as temperature increases, you have a less efficient increase of transport of electrons through this kink, and this leads to this entrapment or buildup, and so you have a just overall least efficient energy transport through this kink. And then, sorry, I missed that one. But so further testing to determine how each different size of the kink affects it differently. And some preliminary testing that I did, it seems that the larger the kink is, the more negative impact it has on energy transport. But I didn't do any sort of testing in the width or stretching of the bond.
Okay, please join me in the there are questions online. If there are, please speak. Oh, there is a question in the class.
If you could go back to like the slide with the movies on them, what's the significance of the green line at the bottom?
So the green line.
Please pass the microphone, otherwise it will be not heard.
So the green line is, so in the non-kinked, it's standard across all of them. And this is kind of modeling the standard like barrier for between each like carbon on a polymer, and each size barrier, whether like that's a specific standardized bond length or bond, I guess not kink, but kind of like angle throughout the whole thing. But when you have a kink, so it's standardized up until that one, and then the kink changes either the length or mostly the length, because it doesn't have as easy of transmission across that. So it models just a non-standardized kind of area in a standardized group of atoms.
Yeah, thank you for the question and the answer. Are there more questions to the speaker? I do have one. It's not like exam style questions. It's more like for analysis and thinking. Would it please analyze the following idea, evaluate whether it is right or wrong, pros and cons. Is it possible to consider the kinked polymer not as one particle in one box, but as two boxes side by side, each of which has its own progression of eigenstates? And then if it is yes, it could be an answer to your degeneracy in the eigenstates. Just please evaluate your thinking of this idea.
I guess you could two boxes side by side.
What are pros and cons of it?
I guess I would say that. So one box standardized with that model obviously fits with the non-kinked. But for the kinked, I guess because of that symmetry, I guess you could picture it or model it as two boxes side by side, because they have that same energy at different eigenstates. I'm not sure how, through my research, how you would go about, I guess, splitting them into and splitting them evenly so there isn't any degeneracy without, I guess, changing the standard model that the non-kinked uses and kind of using either like a two box type of model or something similar.
Okay, yeah, I like your thinking. So, because even if one adopts this idea, the interaction between these two boxes is so strong, they're in resonance, and there will be instantaneous motion of electron from one like ground state to another ground state. Okay, more questions to Wyatt? If no, thank you once again. Yeah, good job. So